Okay, so this is going to be problem number 2, exam number 2, and this particular problem comes from the fall 2012 exam, which you all have access to in the exam module. So we're just going to walk through everything on here like we did the last problem and make sure that we understand how to do everything, okay? So you're going to have a problem with the stress strain curve, and you need to understand, what am I looking at? Well, I know that this is going to be my yield stress, and this is going to be my ultimate stress. I can also look at my shear, and there's my, whoops, drawing the wrong Greek letter, aren't I? Let's erase that back down. This is going to be my yield. I know that the slope of my elastic region in here is G, and I know that the slope of the elastic region here is E for modulus of elasticity. And I have a bar. It's got a cross section. It is 10 inches long, so that's my original length. And this is going to be my original cross-sectional area of area equals 2 times 1.5. Okay. So what is the modulus of elasticity for the bar? Okay, what is modulus of elasticity? Modulus of elasticity, MOE, is just the slope of the line. Okay, it is the slope. It is going to be stress over strain. And so here I'm given this nice curve to work with, and I have 75 KSI divided by 0.0025 inch per inch. And so when I divide this out, I'm going to get 30,000 KSI. And yes, units are important. So the MOE is 30,000 KSI. What tensile force, okay, so a force is going to be in units of kips, will cause the bar to yield? Okay, well, yielding happens here. So I know that the yield stress is 75 KSI, and it is that internal normal force divided by the cross-sectional area. Okay, so if I want to know this internal force here, it's going to be 75 times my cross-sectional area. And we are going to get then that my yield force is equal to 225 kips. And again, you have to use units. What if I wanted ultimate? It would be the same thing. I know that stress, okay, stress is just that internal normal over A. Strain is just change in length over length. Okay, shear stress is that shear force over A. Gamma is that distortion, that shear strain. Okay, so you might just want to mark these on your page. So now, what will the length of the bar be after 250 kips is applied? Okay, so an important thing to note here is we have to understand elastic behavior versus non-elastic behavior, or plastic. If 225 kips causes yielding, if I load it to 250, I am no longer inelastic. I can't just use stress equals E times strain and find our delta that way. Okay, so I'm going to have to actually recognize that we are in this region over here. So the first thing I need to do is I need to figure out, okay, exactly where I am. So if stress, so we're working on part C, if stress equals P over A, and I load it to 250 kips, and I have a cross section of 2 times 1.5, then I'm going to get a stress of 83.33 KSI. So looking at this, I know that that's going to be somewhere in here. Okay, and I can come down just like that. Well, I don't have that value, but what I do have is similar triangles or rise over run, or however you want to look at it. I know this point and I know this point. I know the X and Y coordinates of both of these. Okay, I know the X and Y coordinates of both of these. So I can say 100 minus 75 is to 0.013 minus 0.01 as 100 minus, okay, this stress was 83.33, as 0.013 is to that strain that occurs at 83.3. And so when I work this out, I get that the strain is 0.0109996 inches per inch. And I'm going to make sure, does that make sense? Okay, it should be between 0.1 and 0.13. And that's going to be about 0.0, if we wanted to look at it, 0.011. 0.011. That looks about right. We are about a third of the way over. Okay, so now that I have the strain, I can go back and calculate what the final length of the bar is. Strain equals length final minus length initial over length initial. So I have 0.0109996 inches per inch equals length final minus 10 inches divided by 10 inches. And if I work this out, I'm going to get 10.11 inches. So that's going to be the length when I load it to that point, okay? Which is going to be a lot different value than if you used E. So then the next question says, well, what will the cross-sectional dimensions after 150 kip force is applied? Okay, so now we have to determine, well, if I'm finding cross-sectional dimensions, then I need to know Poisson's ratio. And that was not given anywhere. That was not given anywhere. But I can go back to my sheet, my equation sheet, and I can find that G equals E divided by 2, 1 plus Poisson's ratio. Okay? And I need Poisson's ratio. I've already determined E up here. That was 30,000 KSI. Now I've got to figure out, well, what is G? Well, that's just, okay, that is just the slope of the line in the elastic region on my shear. So I can find that G is 40 KSI divided by 0.0035 radians, okay, 0.0035 radians, and I can come back up, and so we get 40 divided by 0.0035 equals 40 divided by 0.0035 equals, and I get that G is 11,428.5714 KSI. Okay, so now I can come back up in here, and I have 11,428.571. And I have E. And so all I have to do is solve for Poisson's ratio, and I get that Poisson's ratio is 0.3125. So I need that in order to find my new cross-sectional dimensions. So I know as I'm pulling this, I have increased in length. My delta has gotten bigger. So that tells me that I'm going to get smaller internally. Okay, so I need to find the strain that's taking place laterally. Okay, this is the longitudinal and this is the lateral. Poisson's ratio. What does Poisson's ratio equal? Poisson's ratio is negative lateral over longitudinal. Okay, so trying to find blank paper here because I'm trying to recycle as much as I can. Okay, so if I know that Poisson's ratio is negative lateral over longitudinal, and I found that my Poisson's ratio is 0.3125 equals negative lateral divided by longitudinal strain. Okay, if I'm loading it to 150 kips, that is in my elastic region, that is less than the force that causes yielding. So I know in that region what is stress equals E times strain. Well, strain has to equal stress over E, and stress comes from P, right? P over A. So I can calculate that strain. That strain is going to be 150 kips divided by 2 times 1.5 divided by 30,000 KSI. So that's going to be the strain that I'm looking at, and the strain is 0.16, erase, is 1.667 times 10 to the negative third inch per inch. Okay, do you see how I did that? So now I can put that strain here, 1.667 times 10 to the negative third inch per inch. And it's positive because we are getting longer. Okay, so this is where it's just manipulation of the equations that we have. So I can do my algebra, and I get that that lateral strain is negative 5.208 times 10 to the negative fourth inch per inch. And what is strain? Strain is length final minus length initial over length initial. So if I'm looking at my cross-sectional dimensions, I have a starting of 2-inch and a starting of 1.5 inches. So I'm going to have to do this twice. I'm going to have to do it for the width and for the height. So strain, negative 5.208 times 10 to the negative fourth inch per inch equals width final minus 2 inches divided by 2 inches. When I multiply, I'm going to get a negative value, which is perfect because then I'm going to add a 2 to it. So I'm going to have 2 minus, okay, 2 times 5.208 times 10 to the negative fourth equals that final width. And that's perfect because I know that it's actually getting smaller, right? It's actually getting smaller. And I get that my final width is 1.999 inches. It's just a smidgen smaller. Okay, now I can do the same thing. Negative 5.208 times 10 to the negative fourth inch per inch equals height final minus 1.5 inches over 1.5 inches. When I multiply, it's going to be negative. I'm going to add that positive to it, so I'm going to have 1.5 minus 1.5 times 5.208 times 10 to the negative fourth. That's going to be my height final, and I'm going to get that my height final is 1.499 inches. So my new cross section is going to be 1.499 by 1.999 inches. It's important here to not round too soon. If you round too soon, it's going to be very, very hard to determine these. Okay, it's going to be very, very hard. So make sure that you're not rounding too soon, that maybe you're holding that in your calculator so as you come through, you're not rounding too soon and you're still getting a 1.5 by 2 because we know it's going to be slightly smaller because we're in that elastic region. So while we're here, let's just go back and talk about some other things. You could be asked, what is the modulus of resilience? That's just the area. Okay, here, that would be my modulus of resilience. You could be asked for the modulus of toughness, and that's the whole thing. Okay, the whole thing is modulus of toughness. And because we have these nice areas here, you guys can actually solve all of that. And I think that's it for this one.